For over 300 years, the world of geometry was ruled by a single, comforting, and counterintuitive truth. It was a rule that suggested the universe was flexible, forgiving, and full of open space. The rule was this: if you have a convex shape, you can always cut a hole in it large enough to pass a copy of that exact same shape through. It sounds physically impossible, like a magic trick. How can a solid object pass through itself without destroying the structural integrity of the outer shell? Yet, starting in the 17th century, mathematicians proved it was possible for a cube. Then they proved it for the pyramid, the octahedron, and the dodecahedron. By the early 21st century, it became a widely accepted conjecture that every convex polyhedron in existence possessed this quality, known as Rupert's property. It was a mathematical yes, woven into the fabric of spatial reality. But as of late 2025, that rule is dead. Two mathematicians, Jakob Steininger and Sergey Yurkevich, have unveiled the Noperthedron. It is a convex polyhedron with 90 vertices and 152 faces, and it is the first shape in history that mathematically forbids its own passage. It is a self-blocking object. This discovery has shattered a centuries-old belief and opened a new frontier in high-dimensional search algorithms and material physics. Today, on G Fun Facts Online, we are going deep into the story of the Noperthedron, from the royal wager that started it all, to the 18 million block computer search that finally proved our intuition wrong. To understand why this discovery is so massive, we have to go back to the smoke-filled rooms of the late 1600s. The problem wasn't born in a classroom. It was born from a wager by Prince Rupert of the Rhine. Rupert was a man better known for leading cavalry charges in the English Civil War, but he was also a keen amateur scientist. He bet that it was possible to cut a hole in a cube large enough to allow another cube of the exact same size to pass through it. On the surface, this sounds absurd. If you take a cube with a side length of 1 and you drill a hole straight through a face, the maximum width of that hole is 1. A cube cannot pass through a hole of the same size without friction, and certainly not if the hole needs to be strictly larger to allow free passage. But Prince Rupert wasn't thinking in 2 dimensions. He realized that if you tilt the passing cube, orienting it so that one of its internal diagonals is vertical, the shadow it casts is not a square, it is a regular hexagon. And crucially, the width of this hexagonal profile is significantly wider than the square face of the cube. In 1693, the English mathematician John Wallis proved Rupert right. He calculated that if you excavate a tunnel along this specific diagonal, you can fit a cube that is approximately 1.06 times larger than the original. Not only could an identical cube pass through, but a slightly larger one could as well. This 1.06 ratio is now known as the Newland constant, named after the Dutch mathematician Peter Newland, who refined the calculation in the late 18th century. For a long time, this was just a parlor trick. But as mathematics formalized, geometers began testing other shapes. In 1968, the tetrahedron was proven to have Rupert's property, then the octahedron, then the Archimedean solids. The pattern was overwhelming. Every convex shape mathematicians looked at, whether it was simple like a pyramid or complex like a soccer ball, could, with the right orientation, allow a copy of itself to pass through. By the early 2010s, the universal Rupert conjecture had crystallized. The belief was that convexity implies a certain average bulk, meaning there would always be a thinnest angle to look at a shape to create a hole, and a thickest angle to align the passing shape. Nature, it seemed, liked freedom of motion. But science does not run on assumptions. The crack in the conjecture didn't come from a grand unified theory, but from 2 researchers, Jakob Steininger and Sergey Yurkevich, who became obsessed with the problem after seeing an animation of passing cubes in 2018. While most mathematicians were trying to prove the conjecture true, Steininger and Yurkevich began hunting for the exception. They focused on shapes that were too round. Their logic was simple but profound. If a shape is very spiky, like a star, it is easy to find a gap between the spikes. But if a shape is nearly spherical, its shadow is almost always a circle of the same size. There is no skinny side to exploit. Their first suspect was the rhombicosidodecahedron, a shape with 62 faces that looks incredibly spherical. In 2021, they ran simulations showing that the best possible tunnel for this shape was tantalizingly close to fitting a copy, but failed by a fraction of a percent. However, suspicion is not proof. To prove a shape is not Rupert, you have to prove that for every possible orientation of the tunnel and every possible rotation of the passing shape, a collision occurs. This is a massive computational problem. You are dealing with a 5-dimensional search space. You have 2 parameters for the tunnel direction, essentially the latitude and longitude on the shape, and 3 parameters for the orientation of the passing shape, pitch, yaw, and roll. You cannot just brute force a 5D space because the possibilities are infinite. You needed a shape that was mathematically designed to fail. In mid-2025, Steininger and Yurkevich stopped looking for existing shapes and decided to build a monster from scratch. They needed a shape with high symmetry to reduce the number of calculations, point symmetry to simplify the projection math, and, most importantly, chubbiness. It needed to be fat in all directions to maximize its shadow size. They used an evolutionary algorithm to refine the design. They wanted a shape that maximized the size of its smallest shadow while minimizing the size of its largest cross-section. The result was the Noperthedron. The name, coined by Google software engineer Tom Murphy-7, literally means the not Rupert polyhedron. It is a rotund, crystal-like object with 90 vertices, 240 edges, and 152 faces. Structurally, it consists of two large, regular 15-sided polygons on the top and bottom, connected by a complex belt of 150 triangles. It has been described as a low-poly barrel. It lacks the delicate spikes or long edges that typically allow Rupert tunnels. It is a shape designed to be stubborn. Designing the shape was only half the battle. Proving it worked required a computational tour de force. Steininger and Yurkevich developed a local theorem. They proved that if a shape fails to pass through in a specific orientation, it will also fail in all neighboring orientations within a certain small angle. This was the key. It meant they didn't have to check infinite angles. They could check blocks of angles. They divided the 5-dimensional parameter space of the Noperthedron into approximately 18 million distinct blocks. Using a custom-built solver on a high-performance cluster, they tested each block. The computer asked a simple binary question 18 million times. Can it fit here? Block 1, no. Block 2, no, all the way to block 18 million. The answer was always no. The algorithm finished in August 2025. Every single possible geometric configuration resulted in a collision. There was no tunnel, no trick, no magic angle. The Noperthedron was watertight. The universal Rupert conjecture was false. To a layperson, this might sound like an abstract victory, a gotcha in a game of 4D Tetris, but the discovery of the Noperthedron has profound implications for multiple fields of science and engineering, particularly in material science. Think about granular physics, the study of how particles flow and jam, like sand in an hourglass or pills in a bottle. Most particles can slide past each other relatively easily. The Noperthedron represents a maximally jamming geometry. Because it cannot pass through a hole of its own shape, a collection of Noperthedrons is theorized to have unique interlocking properties. Engineers are already simulating aggregates made of Noperthedron-shaped gravel, calling it Nopert concrete. Early results suggest these mixtures form significantly stronger, more shear-resistant interlocking structures than standard crushed stone. If particles can't slide through each other, they are less likely to segregate by size, which is a major issue in pharmaceutical mixing and alloy production. This discovery also challenges our understanding of packing density. The Noperthedron is a bad parker. It doesn't want to slide into tight spaces. This makes it a fascinating candidate for disordered packing studies, which look at how to fill a volume with shapes that refuse to order themselves. Interestingly, the discovery of the Noperthedron coincided with another geometric breakthrough in 2025, the soft cell, a shape with rounded corners that tile space perfectly. While soft cells are about filling space seamlessly, the Noperthedron is about blocking space. Together, they represent a renaissance in shape theory. We are moving away from the Platonic solids of antiquity into a new era of functional, algorithmic geometry. We are no longer just discovering shapes. We are engineering them to have specific behaviors, whether that is tiling, blocking, or jamming. The Noperthedron is likely just the first of many. Mathematicians have now proposed a Rupert spectrum. A score of 1.0 or higher is a super Rupert, like the cube. A score of exactly 1.0 fits exactly. A score of less than 1.0 is a non-Rupert. The Noperthedron has a score of approximately 0.98. It fails to fit by about 2%. Researchers are now hunting for the most Nopert shape possible, a shape so self-incompatible that a copy would need to be shrunk by 10 or 20% to pass through. Additionally, Steininger and Yurkevich are returning to their original suspect, the rhombicosidodecahedron. With the techniques developed for the Noperthedron, it is widely expected that by the end of 2026, it will be confirmed as the second known non-Rupert solid, and the first natural one that wasn't algorithmically generated. There are also questions about higher dimensions. Does Rupert's property hold in 4 dimensions? Can a hypercube pass through a hyperhole in a hypercube? The discovery of the Noperthedron suggests that our intuition about higher dimensions might be flawed. If 3D space allows for self-blocking shapes, 4D space, despite its greater freedom of rotation, might surprisingly have even more restrictively blocking shapes due to complex cross-sections. Ultimately, the Noperthedron is a reminder that mathematics is not just the study of what is true, but the study of what is possible. For 300 years, our intuition told us that space was forgiving, that with the right perspective, any obstacle could be overcome, and any shape could slip through itself. The Noperthedron proves that there are limits. There are shapes so stubborn, so fundamentally solid, that they cannot be perspectived away. It is a shape that says no. As of February 2026, you can actually download the file of a Noperthedron and 3D print it. You can hold it in your hand. It feels smooth, heavy, and unremarkable, like a weird crystal vase. But if you print a second one and try to pass it through a hole in the first, you will feel the hard stop of mathematical reality. The wager is settled. Prince Rupert has finally lost.